Hello guys, this is Darshak Sakarelya. Today I am going to present on the topic of DST chart interpretation and data validation of the DST chart. So this is the topic which I have chosen as a part of our assignment, which is given by our faculty mentor Dr. Gupta sir. So in this video lecture you will be briefly introduced about the DST chart interpretation, and here in this video I have also given one example how to validate the DST data. So you will get some very important aspect of the DST. So I hope you will enjoy it and you will get some information about it.
Hello everyone. Today we are going to discuss about the DST chart interpretation and data validation. So this is the topic which I have chosen as a part of our assignment, which is given by our faculty mentor Dr. Pawan Gupta sir. So hope you will like and you will get some information regarding this. So let's start. So first I will start with introduction. So in generally DST it is drill stem test is nothing but will do temporary completion in the well to determine some formation property like what is the production index, what is the flow rate. This kind of property we can determine, and some property like initial reservoir pressure, like indirect property like permeability, that can also be determined from the drill stem test. It is a type of temporary well completion that is used to evaluate the formation and inspect a reservoir property. So this is basic definition. As I have told that there are some property which can be directly measured, like static reservoir pressure, what is initial reservoir pressure, what is flow rate, what is reservoir depletion. Reservoir depletion generally we can measure by drawdown, because in DST we are allowing the well to flow for some time. So we will measure what is the reservoir pressure after some time, like we have allowed the well to flow for some time. Then after that what is the decrement in reservoir pressure that we will measure. So from that we can determine the what is the reservoir capacity, what is the reservoir flow capacity, that is kh. So this kind of information we can directly determine from the DST. So, and there are some property which can be indirectly measured, like average permeability, what effective permeability. If there is a two phase or three phase, then we can determine the effective permeability. If this is single phase, then it is absolute permeability, as we all know. So and then reservoir pressure, what is wellbore damage during drilling, what is the I mean to say, there are some invasion in the formation due to the mud or overbalance. So what is the damage, productivity index, this kind of all information we can determine from the DST. So there are basically four component in DST tool. First one is a pressure recorder, which is used to measure the pressure data. Second one is test valve, which is allow the oil to flow inside the DST tool. So it is regulated from the surface itself. Third one is hydraulic bypass or equalizing valve, that is used to balance the pressure around the packer. And third one is a packer, that is used to isolate the productive zone, which is interested zone. I mean, we are interested in that zone, we want to measure the property of that zone, so we will isolate that zone using the packer. So these are the basic four components which is essentially required to perform DST. There are also some component that they are known as auxiliary component. We will not discuss these all component here. So our main focus is how to read DST chart and how to interpret that chart. That is very important thing for engineers. So this is a basic equipment, I mean schematic diagram of DST tool, how it is look like and how it is lowered in the formation. Okay. So now coming to the our interpretation, that is our main focusing part. So as we all know that suppose we want to do a DST, then first of all we will pull out the old drill string uh, out of the well, then we'll remove the bit, and instead of bit we'll fit the DST tool. Then after fitting the DST tool, we'll again lower down the whole our testing into the well bore, and after reaching our interested depth, we'll set the packer and all that, and then we'll test our zone. So this is basic process. I mean to say, this is followed during DST. So as you can see in figure, before running the tool into well, the tester insert the test chart into the recorder and draw the baseline which indicate 0 psig. So this is initial pressure at the well head, so that is indicated by blue line, as you can see in figure. Now here well is fully filled with mud. There is no any kind of tubing or any kind of other pipe inside the well, so it is well bore is fully filled with mud. Now we start to lower the DST tool. So it is having a pressure gauge, so it will measure the pressure with depth. As it proceeds further in the well bore, pressure will increase due to hydrostatic head, so it will measure the pressure. So from A we'll start from A, I mean we can say A point as a wellhead. From the wellhead it is going down, down and down, and it will reach at the B point, which is our interested point. Our zone of interest is at is located at B point, so we will stop at B point. um, as you can see in figure that from A to B, pressure is increasing with time due to the hydrostatic head. Now this is the initial phase segment. That segment is indicated in this figure, that is A to B. So after reaching our interested point, we will actuate the packer and we will isolate that zone. Then after stabilizing the pressure, we'll get exact B point. So as you can see in this figure, A to B line is not straight line. So this is straight line is due to some uh, uh, other factor, like suppose in wall is not particularly circular, like it is not having a constant radius r throughout the length of wall. There are some cavities, there are some spots, so due to this radius may be changed. So due to the the change in radius, the hydrostatic pressure can be also changed, because volume can also be changed due to the irregular radius. So volume is changed, so hydrostatic pressure will also change. So there are some uh, not straight line we can get from A to B. So this is indicated like zigzag or this kind of pulses kind of thing. But then there are some also reasons which I have also written here, like surges. I mean to say, suppose we are suppose we are fitting our tubings during the lowering of DST, we are fitting our tubing, so there are some losses of the mods, or due to some other problem we can also get this kind of pulses from A to B. So it is not basically straight line. Then after reaching the B and after setting the packer, the pressure will be stabilized around the packer, then we will get exact B point that is located in figure. Then after that we'll open the test valve. So as we open the test valve, pressure suddenly decrease and come to the atmospheric pressure, because the string is fully open and is at atmospheric pressure, because inside the inside the inside this there is nothing in the drill stream. So due to this, pressure will be suddenly decrease and it will come to the atmospheric pressure at the C point. So we'll allow the now formation fluid to come inside the drill string. So as formation fluid come inside to drill string, um, formation fluid head will increase in the drill pipe. So pressure at the pressure gauge will increase due to the hydrostatic head of the fluid, that is indicated by C to D line. After that, after getting some hydrostatic gauge, we will again uh, provide some time to build up. I mean to say we'll start the valve, test valve, and then build up will occur from D to E. As you can see in pressure, build up will occur with time. So after, so this is what I have discussed. This is reason what I have discussed, right? Initial hydrostatic pressure is recorded relatively at point C, B to C. Yeah, that is C to D. That is flow. Initial flow take place from C to D is around 5 to 10 minutes only. Because as you know that there is an invasion occur due to the mud, so we'll allow to mud to flow in the tubing, so that after second flow we'll get clean fluid from the formation. So initially this C to D time period is only to remove the invasion of the mud from the formation. Okay, now D2 is for pressure buildup. Initial certain period time, that is 30 to 60 minutes from D2 point. Now test now from E to if and final flow period occur from F to G. Okay, now after initial certain, we will again allow the well to flow for some time, and then again the formation fluid will come inside the drill string. Again the column will increase in the drill string, so that pressure at the pressure grade will increase due to the hydrostatic head of the that formation fluid, and that is indicated by the F to G. Like F to G is increases, that indicate that column is increasing in the drill string. So it is indicated now. F now again after the final flow will again allow the well to build up. So we'll shut again the well and then allow for pressure build up. So we'll get G2H curve, that is final pressure build up curve, or a final shutting period time, we can say that. From G to H we'll get this curve, and we can decide this time for certain, like 3 hour or some minutes, as per our requirement, as per company's requirement, what they want to know about the formation. Like if they want deep radius of investigation, if they want deep, I mean to say very deep parameter, I mean to say very deep parameter of the reservoir, like what is the permeability and what is the radius of investigation, and what is the if there is any fracture at the large, that can be known from the this curve. That is from G to H. Now from G to H there is one line which is drawn from the I to H to I. So this we'll discuss later on. So from as I discussed that time required for G2H will depend on the respective company, what they want to know. Now after that after getting the our parameter, we'll close the second valve, the second flow period time. Then we'll circulate the killing mud in the well bore. So after circulating the killing mud, we'll replace the mud which is present with which is present before the killing mud, which will be displaced through tubing. We will inject the killing mud through annulus, and mud which is present uh, previously will be displaced through the tubing, and then wellhead then will separate it. This is the method. So from that after replacing the mud with killing mud, then we'll remove the paper. So at the pressure recorder, again pressure will increase and it will reach to the I point. So it will reach to the I point as shown in figure, and it is approximately same as the B. So now after that we'll slowly remove the drill string. So it will reach from I to J as shown in figure. So this is basically a DST chart which will be getting during the DST test. So now we want to know that this recorded parameter are right, or what is the flow. So in DST we will discuss that. Will I mean to say, we have discussed that we are allowing the well to flow. So what is the flow rate? What is the capacity of well? That parameter can be derived from the DST chart. Or if there is any kind of problem occur during the DST testing, so what kind of problem occur, that can also be investigated. So now here I have demonstrated one simple problem interpreting DST pressure chart. So as you can see that, suppose our packer depth is 4182 feet, gauge depth is 4174 feet, mud density 10.1 pound per gallon. Now all the parameter are given. Initial hydrostatic pressure, these all parameter are I mean are got from the DST chart. So first flow, what is the time for first flow, what is the pressure after first flow, certain time this final, or same for the final flow, what is the final flow period, certain time for final flow, certain pressure for final flow, recovered feet of oil, what is after the first flow, after the second flow, what is the head of oil, what is the head of formation fluid in the district. This kind of parameter we got from the DST. So now we want to validate this data. So how we will validate this? Suppose from the pressure gauge, as you can see here in this figure, from at the B point will be having a pressure at B point. So from DST chart we can get the pressure at B point. Now this pressure is right or wrong, how can we check it? So we are having a mud gradient as shown in this slide, that we are having a mud density, sorry, in this slide, 10.1 pound per gallon. So from rho gh we can calculate the depth at the interested point, like what is the depth at the B point. So at the B point we are having a pressure at the B point. What can, how can we validate pressure? So we are having a mud density, we know the depth of the B point, that is the gauge depth. Actually B point is our gauge, we can tell that. So 4174, that is the depth of the gauge. So from the we are having a formula, that rho gh, from that we can calculate the pressure. First we will calculate the mud gradient. So mud gradient, how can we will calculate? So here we are having a 0.433 divided by 8.33, and this is the constant which is used to convert the pound per gallon to the psi per feet. So we'll get firstly mud gradient. Yeah, this is shown in this slide. Mud gradient is equal to 10.1, that is our mud density, into the that constant which I have told you, that is 0.433 divided by 8.33, it is equal to 0.5247 psi per feet. That is our mud gradient. Now we'll multiply this mud gradient with our depth. Depth means depth at B point. What is depth at B point? That is our pressure gauge depth, that is our pressure gauge depth. So at suppose our B point depth is 4174, so we will multiply this depth with mud gradient and we will get 2191 psig at pressure at B point. Uh, if we see the pressure in DST chart at B point, then we'll get approximately 2314 psig, that is approximately 2191 psig. So both pressure are equal, I mean both are near, there is not much difference between these. So we can validate that this data is correct, which is obtained from the DST chart. So there is nothing happened during DST, I mean while testing the well. So this is approximately same. Our final hydrostatic pressure, mud pressure, is also 2290 psig, which is also approximately 2191 psig, approximate to 2191 psig. So from that we can validate our data. Now we want to know what is the flow rate while testing the well. So our main aim is to know the flow rate. So here I have given some formula to know the flow rate. So there are I mean or we can also calculate the feet of mud. So suppose During the first flow period, we want to know what is a feet of mud. Feet of mud means how much height is, how much uh, length of the dressing is filled by formation fluid when we allow it to flow during the first flow period. So feet of mud during the first flow period can be given as initial setting pressure at the end of first flow period divided by mgr. That is mud gradient. Yeah, or we can also calculate this, basically derived from P is equal to rho gh. So P is um, initial certain pressure at the end of first flow, and rho gh or hydrostatic column head, due to this pressure is due to the hydrostatic column head in the D-string after the first flow period. So from that we'll get H. From that formula we can calculate the H. So feet of mud can be calculated. Then capacity of drill collar is given. If it is not given, then I have given the formula. We can calculate from this formula. Here CS CS is also CS into rho divided by 144. It will give in barrel per feet. CS is Weber coefficient, which is also given here. So basically from this formula we can calculate the drill collar capacity. But here I have taken it as a 0.00607 barrel per feet, so it is already given, so we'll use this. If it is not given, then we can use this formula, then we can calculate. Now we'll estimate the fluid produced from formation, that is FVF. So we'll feet of mud into CDR. CDR is a capacity, drill collar capacity, that is in barrel per feet into feet of mud. So that is in feet and CDR is barrel. So feet will be cancelled and we'll only get barrel. So it gives the volume of the formation fluid that is achieved, or that is filled in the district after first flow period. I mean after first flow. So that volume is FPF. Now flow rate is a volume divided by time. So that volume will be converted into that volume will be in barrel. Yeah, that is volume will get in barrel. So now we can convert into stock tank barrel or surface barrel. If this is taken as a surface volume, then we'll use the stock tank barrel unit. Now that volume divided by flow time. Here flow time will generally in minute, as shown in slide, that we are taking the flow time in the minute, like we are allowing the well to flow for we are allowing the well to flow for 30 minutes, 50 minutes, so this time is in minute. Now we'll convert into day by multiplying it into 1440. Then we can get the initial flow rate. What is the flow rate? So from that we can calculate the what is the capacity, what is the deliverability of the well to deliver the fluid from it. Now okay. Now we'll calculate the flow period for second flow period. I mean to say flow rate for second flow. So at the end of the first flow, pressure was 35 psi. Assuming that all fluid flowing during the time was drilling mud, we may estimate the height of mud column from calculation of hydrostatic mud pressure. The mud exert a pressure of 0.5247 psi per feet of column height. So 35 psi is equivalent to 67 feet of mud. So this is actually we have done. I have told you that how can we calculate the feet of mud. So that for that we have to check the we suppose we will get the pressure after the first flow is 35 psi. Initial certain pressure of the after the first flow is 35 psi before build up start. So from that we can calculate the feet of the mud. So we are having a mud density 0.52% psi per feet. So we'll divide it by mud density and we'll get the feet of the mud. Actually we are supposing here that we'll only get the mud at the initial time. will not get anything, like will not get oil at the first flow. This is our assumption. Or yeah, we can also tell that we'll get the gas mud. Initial flow period, we are having a mud, gas and oil. All three phase can exist. So this can be happen. Now okay, so this is basically given in the slide. So here, how can we will get this data? So we are having that volume of the gas cut mud in the dressing. So when we circulate it out at the surface, we can calculate the what is the volume of that gas cut mud. So that volume we have, and from the calculation we are having a volume of that gas cut mud. So we can compare it and we can check it that validation is right or wrong. That we can do. Now we want to suppose measure the um, flow. I mean to say flow during the second. I mean flow. What is the flow rate during the second flow period time? So as you can okay, so now as you can see that 240 feet of the drill collar were used in drill string. Suppose this is our total length of drill collar. Now capacity is given and 67 feet of equivalent, I mean to 67 feet is of the drill collar is already filled with gas cut mud. So how much volume of gas cut mud is present in the drill collar, which is given as 0.407 barrel. As you can see, we will multiply simply with drill collar capacity and we will get what is the volume of that gas cut mud in the drill collar. Now after that pressure in now during the second flow period time, suppose that pressure is increased from the 35 psi to 145 psi. Now this is a 145 psi at the end of the second flow period. Now as we have the data that to measure oil gravity is 44 degree API specific gravity, from that we can calculate that is 0.806 crore, and mud gradient or gradient of the oil or whatever furnace fluid produce is 0.349 psi per feet. That gradient we are having. Now in here we are assuming that during the second flow whatever fluid is produced is only oil, and now pressure here increase is 144 minus 35, that is 110 psi. So now we can also calculate what is a feet of oil. So we'll simply divide the 110 psi with the oil gradient, that is 0.349. So we'll get 315 feet of oil. As you can see, now we are having a 240 feet of drill collar total. So and suppose we are having a drill pipe and its capacity is 0.01422 barrel per feet, right? So now what is the volume of oil in the pipe? Because during the second flow period some amount of oil is filled in the drill string. So some gas cut mud is also rise up in the drill pipe which is connected to the drill string. So now as you can see that uh, volume of oil in the pipe is equal to 240 feet of drill collar minus 67 feet of mud into drill collar capacity. So that volume, this segment will give the volume of the formation fluid during the second flow period inside the drill collar. What is the volume of that fluid in the drill collar? That will be given from this part, plus 315 feet of oil minus 240 minus 67 feet of oil in drill collar. So total we are having a 315 feet of oil, right? So from that we'll minus it out, this value 240 minus 67 feet of oil in drill collar. So this will give the feet of the oil in the drill pipe, right? I hope you can imagine or you can think it out. So this will give the feet of oil in the drill pipe. Now we will multiply it with the drill pipe capacity, that is given 0.01422 barrels per feet. So this will give the volume of the that fluid in the drill pipe. Also then we'll do summation of both this value and we'll get total barrels of oil record during second flow period time, and then we'll multiply with the time taken for second flow period. Here we have taken 120 minutes, so and then we can get stock tank barrel per day. So yeah, this is the end of our this is the end of my presentation. So I hope you will get some basic information how we will validate the DST data, how we will interpret the DST chart, and how we can use the DST chart for getting some information. And here I can also say that here we are getting the build-up curve. So we can apply the Werner plot, Werner approximation to get some formation parameter like skin, permeability, etc. Because we are having a build-up data. For small period of time, we are having a build-up data in DST. We can apply the Werner approximation and can calculate the other parameter also. So this is how DST is very useful. It is basically carried out in exploratory well, where we are having a new formation. We want to test the what is the formation property of that new, I mean what is the formation property, and all that. If we want to check out the what are the other capacity to deliver the fluid. So this kind of data we can get from the DST. Okay, thank you.